This is a problem 3.8. We have x of t is, we'll do this, and then we're going to switch these two. And you can use definition we'll do for a graphical method. Let's graph this, x of t. So if you graph x of t, before we do that, we want to do e of t first. E of t power of this e function as the positive, so it's increasing. So going, this is e to the t, and also intersection of this signal and y-axis, that is 1. When t equals to 0, e to the 0 is 1. That's how we find that. Now we need to multiply this guy times u of negative t. If we have u of t, we want inside of the parentheses is a positive t, we want positive side. If you have u of negative t, we want negative side. You can look at that way. So u of negative t, we want negative side. So basically, we don't want all these positive side, but this is x of t. And then h of t, we want to have, we saw u of t, I'll just do it again. U of negative t, and then u of 1 minus negative t. We want to look at inside of the parentheses, and we're going to let that equal to 0. That'll give us t equals to 1. So this time, we're going to move this guy to the right by 1. That is u of 1 minus t. We're going to multiply this guy times 2. That'll change the magnitude or amplitude of this u function. Now the height is going to be 2. So this is 2u of 1 minus t. To get the h of t minus tau, whenever we see t, we're going to replace to t minus tau. And that's basically flip this guy over, -1. And then we put t, our h of t minus tau, as the green one is this. And I'm going to move that with the x of t. So this is t minus 1. And the height is 2. And typically what we did, we moved to the negative side of the graph. I can do that. So what if you do, you can do this, and this is t minus 1. Now, the area under the curve for both signal, that is integral lower bound t minus 1, upper bound 0, and we have e to the t, e to the tau d tau. This is from this x of t graph, and we need to check for h of t minus tau, h of t minus tau. Okay. The amplitude is 2. So from there, we're going to multiply this times 2. And that equals 2 times e to the tau, that is from t minus 1 to 0, equals 2 times e to the 0 minus e to the t minus 1. That is 2, 1 minus e to the t minus 1. So now, we're switching these two. So we have x of t equals 2u of 1 minus t. That is that. Now we have h of t equals e to the t u of negative t. We have h of t. Now we want to find h of t minus tau. That is e to the t minus tau. Wherever we see t, we're going to replace with the t minus tau, and u of minus t plus tau minus t minus tau. So when we graph this, flip it, and this, and we let this equals to 0, and this is going to be just a t. Tau equals to t. So this is tau axis. This is h of t minus tau. And we're going to bring this to here. So if the t is some area here, and this is t. T could be anywhere, right? When t is greater than 1, y of t equals to 0, when t is less than 1, now the integral lower bound is going to be t, upper bound is going to be 1. And this is the portion that we need to find from the t, e to the t minus tau d tau. So this time we have x of t as a blue, and the amplitude of the x of t, we need to multiply 2. That equal 2 times integral t to 1 e to the t times e to the negative tau d tau. E to the t is in the t domain, but we need only tau, so that we can treat this as a constant. Take it to the front. That is 2 times e to the t, 1 over negative 1, e to the negative tau from t to 1, negative 2 e to the t, and if you plug it in 1, e to the negative 1 minus e to the negative t, negative e to the t can distribute it, and we have a 2 negative e to the t plus e to the negative t times e to the t, and this is 1, so 2, 1 minus e to the, we can combine this, which is t minus 1, that is the same. Associative property, if we have impulse response h of t and h1 of t, h2 of t, we can switch them around. And then we have the distributive property. We can distribute x of t into multiple h of t, or if you have a multiple h of t, you can factor out x of t. And then causality and the stability, if you are given h of t impulse response, and then we want to find out it's a causal and stable, we need to use this expression, integral negative infinity to positive infinity. Absolute value of h of tau is bounded by any number that is stable and causal. So let's do this, copy this down. So from negative infinity to positive infinity, absolute value of e to the 3t times u of t, and you plug in h of t into this testing formula. Now we have e to the negative 3 tau, u of tau, and then u of tau will give us the lower bound of the integral. So now it's going to go from 0 to infinity, e to the negative 3 tau, only positive side. So we don't need to have this absolute value anymore. Then that equals to that. And it's a just simple integral of the exponential function. And the result is 1 over 3. So it is stable and causal. So we're going to test one more signal. If we have h of t as u of t, then you plug it in h of t in this formula, and u of t will change to the lower bound starting from 0 to infinity. And since we use the u of t or u of tau, now we have only one. Integral of 1 is tau. Tau is from 0 to infinity, will give us infinity. So it's not bounded by any given number. So it's not stable, it's not causal. 3.5, differential equation model. Physical systems are interconnection of the components, devices, or subsystems. Basically, we can model any signal using mathematical formula. And the solution for first order or second order differential equation, book talks about undetermined coefficient technique. It's a little bit different from what we did in the A Math 1. So I just go use the material that we use in A Math 1 to solve this problem. Example 3.11, we have dy of t over dt plus 2y of t, y of 0 equals to what? 4. In our A Math 1 class, typically we go chapter 8 first for the matrices, and then we're getting into chapter 2, first order differential equation, and then chapter 3, higher order differential equation. And for first order differential equation, the first method we saw in chapter 2.2 actually, is a linear equation. I'm going to use that as a first method using linear equation and integrating factor. The step number one, put it into standard form. And it is standard form. And then we need to find integrating factor. That is this guy in front of y of t. So integrating factor, we need to do e to the integral, whatever in front of y of t is a p of t, then put the t of t there. So 2 dt, that equals e to the 2t. And then we're going to multiply this integrating factor to everywhere of the differential equation. That is dy of t over dt times e to the 2t plus 2y of t times e to the 2t equals 2 times e to the 2t. And then left-hand side of the equal sign, all of this is equal to d over dt y of t times e to the 2t, and then right-hand side is this. How? We can just simply apply product rule from here. First derivative, second one, and then first, second derivative of 2e to the 2t, 2 times e to the 2t. So it's just the exact same one. Now we can take the integral for both sides. Then the left-hand side, we have y of t e to the 2t equals to right-hand side, 2 times 1 over 2 e to the 2t plus c. We have a y of t, multiply everything times e to the negative 2t here. Then we have e to the 2t times e to the negative 2t plus c times e to the negative 2t. That equals to 1 plus c e to the negative 2t. Now we're going to use initial condition y of 0 equals to 4. 4 equals 1 plus c. E to the 0 is 1, so c is 3. Our answer, y of t equals 1 plus c e negative 2t. Second method, just like what we showed in our textbook, undetermined coefficient technique. So for undetermined coefficient technique is from chapter 3, section 4, I believe. What we need to do, we need to find y of t, that is yc of t plus yp of t. Yc of t complementary solution, yp of t a particular solution, and yc of t, we're going to use left-hand side of the differential equation, and then yp of t, we need to use right side of the differential equation. So left-hand side, we have dy of t over dt plus 2y of t, and we let equals to 0. So make it homogeneous equation. We're gonna do d over dt as a m, d squared over dt squared as an m squared, and so on. To find our auxiliary equation, called aux equation, it's gonna be m plus 2 equals to 0. From there, m equals to negative 2. You have a m equals to negative 2, then we can find yc of t equals to c e to the negative 2t, whatever the m value. If it's a second order differential equation, if you have two different m values, then c1 e to the m1t plus c2 times e to the m2t. So this undetermined coefficient is it works really well in the higher order differential equation. And this linear or the integrating factor approach only works with this first order differential equation. So we got yc of t. Now yp of t, we need to look at the right-hand side of the differential equation, which is equals to 2. If it's 2, the constant, we're going to let that equals to a. If the right side is t, then yp is going to be a t plus b. Really depends on the right-hand side. If the right side is equals to e to the t, for example, then yp equals to a times e to the t. So we need to look at the right-hand side. We're going to fit this into this. So we have a y dy over dt. So we need to have a yp prime of t, which is 0, and plug this into original equation. So we have in the original equation dy of t over dt plus 2 y of t equals to 2. dyp over dt is 0 plus 2 times y p of t. We set a equals to right-hand side, which is 2. From here, we have a equals to 1. So the solution is going to be y of t equals yc of t plus yp of t. Yc of t, we say c e to the negative 2t plus yp of t, 1. And that's exactly the same as this guy. And you've used the initial condition, we end up getting the same answer. So stability, you don't have to copy this down. Nope. So any given differential equation, we let left side equals to 0 for the ox equation and find the roots of that ox equation, and the roots are in the negative real axis. So just like for this one, it's a negative 2, right? For this, the negative 2 is somewhere, then it is a stable. And it's a second order differential equation and ox equation giving us negative 5 plus minus j2, the complex number. As long as real portion, sigma is a real portion fall on the left side, meaning the negative value, they are all is a stable. On the real axis, when you plot it, it looks like this, approach to the 0 in this case, stable. And if you have complex conjugate and you plot it, it's going to fluctuate a little bit, but it's going to eventually close to one value, which is stable. However, if the real part is the positive side, then it's not, it's going to go up, it's unstable. And the roots are just pure imaginary portion, plus minus j5 on the j omega axis, then we call marginally stable. So we're not going to really talk about that in this class. So you will see this again in control.